beta, you call that, if you call minus 3 gamma, call that B, you can see that the set of linear combinations is just this ax squared plus bx plus c, and that's something that we've got a really good understanding of, right? Those are just polynomials of degree 2 or less. And over here, right, question 5, this is maybe a little bit more complicated. We do the same thing, linear combination of these two vectors, and here the vectors are binary codes of length 3. Does anyone have an empty seat next to them? Just stick up your hand. So there's one over here, and a couple there at the back. But if you can't find seats, you can't sit on the floor. I have to kick you out. It's a health and safety violation. Run, right? If you can't find a chair, you're going to get kicked out. Lord of the Flies. No, don't sit down. Don't sit down. Off you go, Menzies 10 if you don't have a chair. If you don't have a chair, you're going to Menzies 10. And then over here we just take, we do the same thing. We take linear combinations of these two vectors. And what we might notice about these two vectors is that both of these vectors, the third component is equal to 0. And there's not any way to take a linear combination of these two vectors and get anything other than 0 in the third component of this code, right? By choosing alpha and beta appropriately, we can make these first two entries whatever we want, but there's no way to get anything other than 0 at the end over here. All right. So what we're going to talk about today are systems of linear equations, and we might also have time to start speaking about linear transformations, and we'll speak about what is it that makes a transformation, or what is it that makes a function a linear function. So we'll start with the definition of a system of linear equations. All right, so we'll put this up here, definition. A system of linear equations system of linear equations, and I guess I'm sometimes going to just initialize that as sol instead of writing it out every time, is given or is just the following. And now we want to use color in some sort of sensible way. So it'll be A11 multiplied by x1 plus A12 multiplied by x2 plus A13 multiplied by x3 plus A1n multiplied by xn, and that'll be equal to, let's call it b1, right? So that's just an equation, and it's a linear equation, because these unknowns, generally these x1s, x2, all the way up to xn's, are these unknowns appear linearly. It's just x1 raised to the power 1 with some coefficient in front of it. There's no x1 squared, there's no sine of x2, there's no square root of x3. This is just a single linear equation, and we could have another one over here, although now we have to just change some of these indexes. Okay, and this index here. Right, so this is now a second equation. We 2, 1, 2, 2, all the way up to 2n. And we can have a whole bunch of these equations. Let's actually write the last one in by hand. Oh, sorry, no space. Go to Menzies 10. This is AM1 x1 plus, okay, let's skip lots of this. AMN xn and we bundle these all up together and we say we've got to find values of x1, x2, x3 all the way up to xn that satisfy all of these equations at the same time, right? So this over here is a system of linear equations, and this is a very sort of a long-winded way of writing down a system of linear equations. There's a shorter way of writing it down, a more compact way, where we can just use sort of matrices and vectors to do it. So matrix multiplication is actually sort of defined to make this following thing make sense, right? This, we can write it more compactly. So we can write it more compactly in the following way, just AX is equal to B, where this matrix A over here is a matrix whose entries are going to be A11, A12, A1n, A21, and so on, A2n. No, sorry, there's no space. No space. Menzies 10. Go to Menzies 10. M1 all the way up to AMN. Okay, so we write that. That will be our matrix A. Then our vector X. This is X1, X2, Xn. And our vector B, B1, B2, down to Bn. Okay, so we can write down a system of linear equations very compactly using this following matrix notation. We say that a system of linear equations, or maybe this matrix equation over here, we say that it is a consistent system of equations if there are some values for x1, x2, all the way up to xn. Alternatively, if there is some vector x which satisfies it, right? If there's at least one solution, we say that it is consistent. If there are no solutions, we say that it is inconsistent. Let's put this up in green. That's a definition. So if AX is equal to B has at least one solution, sorry, that must be green since that's what we're defining. It is consistent. And if it has no solutions, we say that it's an inconsistent system. So if you just think about the two systems over here, let's just put up some examples of a system which is consistent and one which is inconsistent. If we think about this system over here, let's say x plus y is equal to 4 and 2x plus 2y is equal to 8. This is a consistent system of equations, and in fact it turns out that it has an infinite number of solutions, and the solutions are all of the form, call x equal to t. Then y will just be equal to 4 minus t, and you have an infinite number of solutions. Okay, let's say is consistent. And in fact, has inconsistent. It has infinitely many solutions. xy is equal to t 4 minus t. But on the other hand, if we write down a system like this, let's just say x plus y is equal to 4, x plus y is equal to 5. That's inconsistent, right? There aren't going to be any values of x and y that satisfy both of those equations at the same time, because that would mean that 4 is equal to 5, which is clearly nonsense, right? So one of these is consistent, infinite number of solutions. It only needs one to be consistent. This particular one has infinitely many solutions. And this over here is inconsistent. It doesn't have any solutions at all. Any questions about that, about this? So the first result, which is maybe going to, yes, question. Well, okay, so if x is equal to t and y is equal to 4 minus t, you get t plus 4 minus t is equal to 4. So on the left hand, the plus t and the minus t cancel, and you just get 4 is equal to 4. And if you substitute it in over here, you get 2t plus 2 times by 4t. So you get 2t plus 8 minus 2t. The 2t's cancel, you get 8 is equal to 8. Right? So that's just a solution. And you should be able to write down solutions to systems of linear equations like this. I mean, simultaneous equations. You did this in grade 11. All right. Yes, question right at the back. What do you mean single value of solutions? No, I mean, so I could take, for example, x is equal to 1 and y is equal to 3. X is equal to 2, y is equal to 2. They're two solutions. Sorry, we don't have any seats. You'll have to go to Menzies 10. Or x is equal to minus 5, y is equal to 9. Any of those combinations will work. So there are an infinite number of combinations for x and y which work. All right. So the first result that we have in this course, and we're going to call our results facts, and this sort of links what we're doing at the moment with what we did yesterday, and this is fact, I think it's 1.1. And this is really just rephrasing something that we already know. It's that the matrix product, or the product, this product AX is a linear combination of columns of A. Just a linear combination of the columns of A. And what I mean by this is that if I were to take, I guess we can write out A11, A12, all the way up to A1n, multiply this by x1, x2, this will be xn, and this will be down to A rho m if we do this multiplication, right, one way of thinking about the result of the multiplication is the following. You're going to get A11, A21, all the way down to AM1 multiplied by x1 plus A12, A22, all the way down to AM2 multiplied by x2 plus, and then we add a whole bunch of things, all these columns, and let's just see, this is a A1n all the way down to AMN multiplied by xn. And why is this the case? Well, this really just follows immediately from the definition of matrix multiplication. If we think about what happens when we do matrix multiplication, right, you're taking this row multiplied by that column. So the important thing to take away from just this first matrix multiplication is that the contribution to the top left term, right, we're sort of going to have an A1 multiplied by an x1. So we have an A1 multiplied by an x1. Okay. And then if we were to take this next row multiplied by this column, we'd have this term here. Sorry, there's no space. Excuse me. There's no space here. You'll have to go to Menzies 10. You'll have that entry over there, which would be A21 multiplied by x1. So that would be A21 multiplied by x1. And you'd keep going down all the way till you reach the bottom here. And this times by this, you'd have AM1 times by x1, which would be AM1 times by x1. So this is just another way of writing out matrix multiplication. And you should understand that when we do matrix multiplication, the result, the product of A multiplied by X, is just a linear combination of the various columns of the matrix A. And this turns out to be a really useful way of thinking about matrix multiplication. And we'll keep coming back to this later on in the course, right? A couple of times we'll use this to prove some other things. Okay, so let me say, sorry, there's no space. Go to Menzies 10. Okay, so that's that was fact 1. And let's take a look at fact 2. So fact 1.2. Fact 1.2 is the following. A system AX is equal to B, the system AX is equal to B, so this system of linear equations AX is equal to B is consistent if and only if that column vector B can be written as a linear combination of the columns of A. And that follows as a direct consequence of the fact that multiplication is just a linear combination of the columns of A. Right, so the system AX is equal to B is consistent if and only if. And when we write if and only if, this is sometimes abbreviated in the following way, or shortened to if with a double F. So if you ever see if with a double F, it means if and only if. It's not just a necessary condition, it's also a sufficient condition. System AX is equal to B is consistent if and only if B is a linear combination of the columns of A. And this isn't going to get a proper explanation beyond the fact that it sort of follows immediately on from the fact 1.1 that we've just discussed. Okay. Later on in the course, when we have more complicated sort of facts, we'll actually write out some explanations, but this I think is something which you should be able to puzzle out by yourselves. All right. Any questions at this stage? Okay, so we're going to keep talking, and one of the things that we can think about is this product AX. Okay, so we've seen this product AX, and we can understand it in a couple of ways. One of the ways that we can understand it is as a linear combination of the columns of A. We can also understand AX as representing that sort of really big mess on the left-hand side in a system of linear equations. But there's another way of thinking about AX as well, which turns out to be really useful. We can think about AX as representing sort of the linear transformation of a matrix X under a map A. So we can think of AX as being a vector which has been transformed from X, and possibly transformed from M into Rn. So let's write out some of this. The product AX this product AX can transformation of the vector X by a so that, I guess there are a couple of things I've written down here. You can think of AX as representing some sort of transformation of a vector. And you would have seen a little bit of this last year, right? You should have seen, 2x2 matrices representing transformations of the plane. So for example, if you have a 2x2 matrix where the entries are cos theta minus sine theta, cos theta, that represents a rotation, an anticlockwise rotation, by theta of this plane, right? So we can think of matrices as representing some sort of transformation, and if a matrix is an m by n matrix, you can think of it as taking in some vector. Okay, that should be a vector x, not just a... You can think of it as taking in some vector x which belongs in Rn, and transforming that into a vector which lives in Rn. So if you're looking at square matrices, where the number of rows and columns are the same, then it's a transformation from one space back into that space, right? So the 2x2 matrix takes the plane and somehow transforms it back into the plane, be it a reflection or a rotation or dilation or a compression or something. But we could also have transformations from higher dimensional spaces into lower dimensional spaces or vice versa. So for example, if you take something in 3 dimensions, you just take any object in 3 dimensions, for example, and you shine a light at it, and you look at its shadow is 2-dimensional. So there's some sort of mapping between the object and the object's shadow, between a 3-dimensional object, a 3-dimensional space, and its shadow, which is a 2-dimensional space. So we can move from one space to another. All right. We have matrices doing these transformations, and the really nice thing about matrices is that they turn out to represent what are called linear transformations. So let's write down the definition of a linear transformation. Turns out that linear transformations are really nice to work with. Okay. So we say that a transformation from, I'm going to say Rn to Rm, in general it can be from any vector space to any other vector space. But maybe we'll start by thinking about Rn to Rm. We call it linear if, and there's sort of 2 conditions that must be fulfilled. The first condition is just that if you take the transformation of the sum of 2 vectors, right? So we take these 2 vectors x and y that belong in our domain, they belong in Rn, you add them together, and then you transform them. That's the same as if you were to transform each vector separately and then add them together. And that should be, so this is for every x and y in Rn. And then the second condition is that if we do our scalar multiplication, and this should be for every, these are vectors, for every x in Rn and alpha in R. Okay. So the thing which makes a linear transformation linear is that it respects the structure of the vector space, right? We said that the thing that makes a vector space is that it's closed under vector addition and it's closed under scalar multiplication. So the structure that we impose on a vector space is the structure given by vector addition and the structure given by scalar multiplication. And a linear transformation is just a transformation which preserves this structure, right? It doesn't matter whether we do the vector addition first and then transform, or whether we transform each vector separately and then add them together. And the same with scalar multiplication. So that's why it's nice to work with linear transformations on vector spaces. Because in some sense, it doesn't matter whether you do your calculations in your first vector space or your second vector space. You'll get the same answer, right? Let me actually just make a remark over here. So remark, more generally, we could have T from some vector space U into some other arbitrary vector space V. It doesn't have to be Rn and Rm that we work with. At the moment, we'll think about Rn and Rm because we're working with matrices, and linear transformations Rm and Rn can be represented by matrices. In general, you can't represent linear transformations between arbitrary vector spaces by matrices, but certainly over here we can. So let's just actually make another remark. Linear transformations are nice. Let's just say linear transformations respect the structure of the vector space. So if we have, let's just draw a really sort of very abstract picture, I suppose. If I've got two vectors over here, let's call this vector x and this vector y. What we could do is we could say, well, I'm going to combine these two vectors in some way, and I'm still in this same vector space. So I add these two vectors and I get x plus y, right? And then I take this resulting vector x plus y, and that gives me some output, which is the transformation of x and y. On the other hand, I could take this vector x, and I could transform it, and I get the transformation of x. And I could transform y, and I get the transformation y over here. And then if I add those two transformed things, I end up actually at exactly the same place, right? That's what it means for a transformation to be linear. It doesn't matter if we do the addition here and then transform across, or whether we transform and then add, we end up with the same result, right? So this would be u, this would be some vector space v. Okay, so linear transformations are nice to work with. They respect the underlying structure of the vector space. They preserve vector addition, they preserve scalar multiplication. Linear transformations from Rn to Rm have matrix representations. I guess this is just a repetition of something I wrote earlier. I said over here you can think about that product as representing a transformation. Let's write it down here again for completeness in the other direction. Linear transformations have matrix representations. So this is something which actually runs in both directions. You can think of every matrix as representing a linear transformation between Rm and Rn, between Rn and Rm, and you can think of every linear transformation between Rn and Rm as having a matrix representation. There's exactly a one-to-one correspondence between them. So let's take a look at an example. And the example we're going to look at is the following. We're going to try to write down a matrix representation for a linear transformation. I'll be with you in a moment, given some information about how it transforms certain vectors. Okay, so let me just scroll up and then you can ask your question.
Does the matrix representation, is it size limited or can it be any size limited?
Well, no, okay, so your matrix representation, the size of that matrix will depend on the dimensions of these spaces. So if you've got a matrix which is going from R5, if you've got a transformation which is going from R5 into R2, for example, then your matrix will be a 2x5 matrix. Okay, so the size of the matrix, the dimensions of the matrix, will always correspond to the dimensions over here of the domain and your codomain, the sort of the inputs and the outputs. Okay, so write down, here's the question, or here's the example we're going to do. Write down write down the matrix representation of the transformation T T is a transformation from R2 to R2, so we're going to have a nice small square matrix. We're just looking for a 2 by 2 matrix. The transformation T that sends, that satisfies, rather, let's say that satisfies T acting on the vector 1, 0 is equal to 1, 1, and T acting on the vector minus 2, 1 is equal to 0, 2. Okay. So we have a transformation. In fact, let's see, I need to explicitly say over there linear transformation. Sorry. So we have a linear transformation. We're told some information about this linear transformation, which tells that it goes from R2 to 1. And more specifically, we're told where it takes this matrix 1, 0, it sends 1, 0 to 1, 1. It sends this matrix over here to 0, 2. And so the question is now, what matrix represents this linear transformation? Okay. Are there any questions at this stage? So one of the first things that you might be thinking, maybe one of the first things that you could sort of ask yourself is this actually enough information to uniquely determine a linear transformation, right? Is it not the case that there might be a whole bunch of different functions, that satisfy these two conditions? They send the vector 1, 0 to 1, 1, and they send the vector minus 2, 1 to 0, 2. If we just have this information here, is it enough to know about how every single vector in R2 is transformed? So is it, right? Is that enough information to know how an arbitrary vector xy is transformed by the matrix, or rather by this transformation T? Yeah?
If you don't have enough information, would you still be able to get a general...
If you don't have enough information, you might be able to find some entries in the matrix, but you won't be able to find all of them. So for example, this turns out to be enough information, but if I only gave you that first bit, you'd be able to find 2 of the 4 entries, but not all 4 entries. Okay. But why is this enough information? I've sort of given that away, but yeah.
I think it's because you're working hard to get each cases.
Okay, so it's got something to do with the fact that we've been given 2 pieces of information, and these 2 pieces of information we're working in R2, there's some sort of dimension thing there, and that's right. I mean, there's a sort of something that we've got to worry about, which is maybe we end up in trouble if we're given the wrong 2 pieces of information. But one of the things that we did yesterday, one of the examples we looked at yesterday, we said, what are all the linear combinations of the vector 1, 0 and minus 2, 1? And we said that if we took all the possible linear combinations of 1, 0 and minus 2, 1, we could actually reach an arbitrary point in R2. Okay, so let's actually just remind ourselves of this. Okay, yesterday, we said the following. So yesterday we said that an arbitrary point in R2 can be rewritten in the following way. We actually went a little bit further and we calculated the values for alpha and beta. I think we said beta is y and alpha is x minus 2y or x plus 2y. Must be x plus 2y, right? But the important thing is that an arbitrary vector xy can be written as a linear combination of these 2. So if you want to know how this arbitrary vector xy transforms, well, the arbitrary vector xy is transformed in the following way. It's just transformed in the same way that alpha 1, 0 plus beta minus 2, 1 is transformed. And since we said that t is a linear transformation, this is just going to be alpha times by the transformation of 1, 0 plus beta times by the transformation of minus 2, 1. Okay? So the transformation of an arbitrary point xy is determined entirely by the way 1, 0 transforms and by the way minus 2, 1 transforms. Okay, so this is actually enough information to solve the problem. Let's write that down. So we can say something like this. So the transformation can be determined. Transformation can be determined from the given information. It's not the case that there might be many different transformations that all satisfy these same two sort of conditions that we've written down. So let's actually, yes?
Would it be a lot harder if the first one was 1, 1, not 1, 0?
I wouldn't say a lot harder. It would be harder. We'll see in a moment exactly what's going to happen, but the fact that that first one is 1, 0 means that the arithmetic we're about to do is easy arithmetic. Conceptually, we'd still do exactly the same thing if it was 1, 1, but it means it gets a little bit trickier. Okay, so the transformation can be determined from the given information. So let's actually do this, right? So let A be the matrix representing T. We want to calculate 4 entries of A, so i.e. A is equal to, let's just call it A, B, C, D. If I was feeling less lazy, I'd write down A11, A12, A21, A22, but I'm lazy. So just A, B, C, D. We want to find these 4 entries A, B, C, D. How are we going to do it? Well, we know the following, right? We know that T transforms 1, 0 to, what do we say, 1, 1. Yeah, to 1, 1. T transforms 1, 0 to 1, 1. So that's exactly the same, right? This is completely the same as saying A, the matrix multiplication of A with 1, 0 is equal to 1, 1, right? The matrix A is the matrix that represents T. Instead of saying the transformation of 1, 0, we can say the matrix multiplied by 1, 0. And we know what A multiplied by 1, 0 is. A multiplied by 1, 0 is AC times by 1 plus BD multiplied by 0. And that must be equal to 1, 1. Right, so there I've just used the fact that matrix multiplication is a linear combination of the columns of A. All right, so we know that the matrix A must actually be the matrix, so therefore A is equal to, so A is equal to 1, C is equal to 1, B and D we still have to determine. All right. B and D we still have to determine. You've got go ahead and try to determine the values B and D using the information, the second piece of information that you're given, but you'll use the same basic principle here. The manipulations are a tiny bit harder because instead of the vector being 1, 0, the vector is now minus 2, 1. But I have every confidence that you'll manage.
A
Okay, so I'm going to very quickly just finish this off. And you could write down something like this. You'd say, well, T, the transformation of this vector minus 2, 0 is equal to 0, 2. And that is obviously completely equivalent to saying that the matrix A multiplied by minus 2, 1 is equal to 0, 2. And now if we take A multiplied by minus 2, 1, we know that that's going to be really a linear combination of the columns of A. So that's minus 2 multiplied by 1, 1, plus 1 times by BD is equal to 0, 2. And now you can solve, you can see that B is going to be equal to 2, D is going to be equal to 4. So our matrix A is equal to 1, 2, 1, 4, like so. Yes?
So when you write this out, set up the test or something, can you go straight to writing 1, 1 to be able to use A's?
Well, you could go straight to 1, 1 like that. I think it's pretty easy to understand where it's coming from. All right. Again, I'm going to hang around, so if you've got any questions, you can come and speak to me at the front. Otherwise, we're done for today.